0, x of 0 and y is 1. Okay. So I have this basic ODE for my fluid particle, but of course the whole point is to characterize the U, to find an equation of the U, to know exactly the dynamics of my fluid particle. Okay? So basically, the Euler and the Navier-Stokes equations will be modeling the variations of U. That's so we now want to know how to find the appropriate PDEs to describe the U. And of course, as often in physics, you use conservation laws. So what conservation laws? So the first conservation that you express is for Euler and Navier-Stokes, the conservation of volumes. This is not a physical principle. This is an assumption. Okay? When you model the fluid by the Euler or the Navier-Stokes equation, you assume the fluid to be incompressible. Incompressibility assumption. Volumes change shape, but they do not change. So how can you express incompressibility? The natural way to express it is saying that this flow is volume preserving. Okay, so incompressibility will mean that the Jacobian of this flow will be 1. Okay, so the determinant of dy of x dy will be 1 at all time. So let me call this quantity small d of t and y. Okay, that's the definition here. The determinant of my Jacobian matrix should be 1. Alright, so what I call dyx is just the matrix dxi over dyj, with I and j between 1 and the dimension d. So that's the first way to express incompressibility. But there is another way, a way to express it on U. Why? Because you have this dynamical system for x. You differentiate with respect to y. Yes, you differentiate this with respect to y. This is ODE here. You differentiate this ODE with respect to y. You get that d over dt of dyx is dxu, the Jacobian matrix of u, times dyx, the Jacobian matrix of x. And so you see that this Jacobian matrix satisfies a linear system. Okay? So it's like d over dt of m equal a of m. And what you want is an evolution equation for the determinant. And you know, this is UV theorem. You know that the determinant follows a very beautiful, a very simple equation, very simple ODE. So its time derivative is given by the trace of A times the determinant of M. That's famous ODE theorem. So if you apply this theorem here, what you get is that the determinant of dys, that I call small d, so d over dt of my Jacobian, will be the trace of the matrix dxq. But what is the trace of the matrix dxq? It's the divergence of u. Okay, so this will be okay. So this is the divergence of u times d. And the divergence of u what is it? It's a definition. It's the trace of the Jacobian matrix, so that's d1 u1 plus d u d. Everybody can read here. So you see here that for this determinant to be constant equal to 1, you need, it's necessary and sufficient condition, the divergence of u is 0. Okay, so that's my first equation. The divergence of the velocity field should be 0. Okay, that's one of the equations, both in Euler and Navier-Stokes. That's the first thing. And so that was given by my first conservation law. Okay, conservation of volumes, incompressibility. Then we can express the conservation of mass. Right? So you take some arbitrary volume V. You say that this volume is transported by the flow. Okay. The fluid particles in this initial volume are moving. And the total mass of this volume, when it's transported, should not change. It's conservation of mass. So you express that the time variation of the mass inside the transported volume, so transported means you look at the image of this initial volume V by the flow, you look at the total mass contained in this transported volume, and its time variation should be 0. That's conservation of mass. So from this, what can we get? So you see, you have a time dependence here, you have a time dependence there, so there is a little computation to perform. And so I leave you as an exercise to check that this time variation is the integral over the same volume of dt rho plus the divergence of rho U evaluated in G and X integrated over X. Okay, so remember, rho is a scalar quantity, U is the velocity field, okay, and the divergence of this velocity field is a scalar. Okay, so everything here in this line is scalar. And remember that divergence of U is 0. So when you apply the divergence to this rho U, you can simplify a little more, and you can say that this is the integral of dt rho plus U dot grad rho. And what is U dot grad? So U dot grad is just U1 d1 plus U d dt. That's an operator. So you have this new constraints, this conservation of mass, and this gives you another equation. This gives you another equation which is just dt rho plus U dot gradient of rho is 0. That's a transport equation over on the density. Okay. But for the Euler and Navier-Stokes equation, we will make some simplifying assumption.